In the previous video, we derived the Newton-Cotes quadrature formula. Using different value of n in this will give us different method to compute the integration. We first put n equals 1 in this formula, so xn becomes x1. On further simplifying, we get the following result. This was the integration of the interval x0 to x1. Similarly, we can compute the integration of all of the small interval, which will be as follows. The integration of fx from x0 to xn can be divided into tiny intervals from x0 to xn. So we can write the integration of f of x from x0 to xn equal to sum of integration in this interval as follows. Replacing it with the result we got previously for the small ranges, writing it collectively, we get the following result. This is known as the trapezoidal rule. Now, let's move on to understand the geometric significance of the trapezoidal rule. What we have basically done is replace the curve fx with n straight lines. Let's look at it visually. Consider a function fx as follows. Now we label the point x0 and x1 on the x-axis. The corresponding y value will be y0 and y1. So the points on the curve are x0, y0 and x1, y1. Now we draw a straight line joining these 2 points. You can see that we have constructed a trapezium. Now the area bound by the curve fx in the range x0 to x1 can be approximately written to be equal to the area of trapezium. The area of trapezium is equal to half times the sum of parallel sides into distance between them. So we have the area to be equal to half times y0 plus y1 times h. This is the same expression we got from our formula previously. So to have the integration from x0 to xn, we have to construct the straight line joining these points and add the area of trapezoid so formed. While we were calculating the integration by taking the area of trapezoid, we can visually see the difference from the area bounded by the curve fx. Now we'll go on to estimate the error that we get on using the trapezoidal rule. We first expand f of x around x equals x0 using Taylor series. Now integrate both sides over x from x0 to x1. After integrating and putting the limit, we get the following. Next, we will replace x1 minus x0 with h. We obtain the following result. We'll call it equation 1. We'll keep this aside for a moment. Now let us expand f of x0 plus h using Taylor series around x equal x0. We obtain the following. Now here we have the trapezoidal formula in the interval x0 to x1. Now we substitute the value of fx1. On further simplifying, we get the following result. We will call it equation 2. Now we'll subtract equation 1 and equation 2. In the left side, we have subtracted the area of trapezium from actual area bound by fx. So this result is basically the error. We can ignore the higher power of h as h to the power of 4 will have very little contribution. So our error in estimating the integration in the interval x0 to x1 is equal to h cube into double derivative of fx at x0 upon 12. Now we will proceed in a similar manner to obtain the error in all the intervals, which on adding together will give us the total error. Now in the bracket we have the sum of double derivatives at points x0, x1, x2 till xn minus 1. Now assume that the point xm among these points at which the double derivative gives the maximum value. To find the maximum possible error, let's replace all of the terms with double derivative of fx at xm. So the error will be less than equal to h cube n times double derivative of fx at xm upon 12. Now as h equals b minus a upon n, thus we can simplify it to the following. This is the maximum possible error we can get. In the formula for error, we can see that error is proportional to q of h. Thus on decreasing the spacing between the point, that is if we increase the number of points we take within the range we have to calculate the integration, the error shall decrease. Here you can see the function sine of x upon 2 plus 3. We will be estimating the value of integration using a trapezoidal rule and also find the error. The actual value of integration in the range 1 to 8 is equal to the following. We first take the number of points within a range equal to 3. Let's increase the number of points to 10. You can see that the error is decreasing. As we take more number of points, the error will keep on decreasing. So yes, that's the end of the video.